Good morning, good afternoon, or good evening. This is now question 2 of the 2024 Step 2 paper. Now, as I've said at the beginning of each of these, you should only be watching this video if you've already had an attempt at this question. If you're watching this for spoilers, you lose all benefit of attempting the question yourself. So either you've already completed this question and you're looking for some further hints on other ways to think about and to work through this particular question, or you've given it a good hour or so and you've got yourself stuck and you're now looking for some hints. As always, if you do get a hint while watching this video, please do pause it, try the question again using that hint, see how much further you can get before continuing watching the video. Unfortunately, this is a question which I have spoilt for myself. I did do this question a few weeks ago. I don't have the solutions right in front of me. I'm not just copying out a solution I've already got, but I have already gone through the thought processes required to complete this. Saying that, I will, of course, try and give you the same kind of first thoughts that you should be having while tackling a question such as this. So let's look to it. We've got 3 parts of the question. All 3 parts are dealing with what looks like a really horrendous summation and linking it, at least in the first 2 parts, and you could probably guess in the third part too, linking that summation to an integral. So as we're going through, we should be thinking, how can we use the previous parts? Will the previous parts actually help us to do the later parts? And already, if you're glancing at part 2, you can see the summation on the left is very similar to the summation on the right for different values of m. So it looks like part 2 is just going to be using part 1 multiple times. And then the final part, well, who knows? You might already be able to get some intuition, some guess on how to do that summation. We'll talk more about it when we get there. But let's start with part I of the question. So in classic step style, they're asking you to do something which is actually well within the realms of your normal A level. We're trying to expand 8 plus x cubed to the minus 1. Well, using the binomial expansion, we have to write this as 1 plus, not 8 plus. So I'm going to factor out that 8. As the 8 gets factored out, it gets hit by the power of negative 1. So I'm actually having an 8th outside. And already I'm starting to look at what the answer is. I can see in the answer a 2 to the power of 3. I've got a 3k, sure, but I've got a 2 to the power of 3 as well, which is that 8 that we pulled out. So maybe already I'm starting to feel quite pleased. So expanding this out, using the binomial expansion, we're getting an 8th out from front, 1 plus n, and then the thing to the power of 1, plus n minus 1 over 2, the thing squared, etc. Now again, I'm looking to the answer, I'm looking to the next part of part I, and I'm noticing that I'm going to want a general term. I don't really care about the first, second, third, etc., but I do want the general term. So whereas normally I would stop here with this dot, 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 I am also going to try and write down what the general term is going to be. So it's going to have minus 1, minus 2, a load of stuff up to something. And I'm going to put the thing to the power, I'm going to take suggestion from the question, to the power of k. So now I want to compare and try and work out how this thing links with what's going in this bracket here. And if I look back, I had a 2 here and I went down to negative 2. When I had the power of 1, I went down to only negative 1. So it appears that bracket is exactly just negative of the power over, well, the first term was over 1 factorial, then over 2 factorial, over 3 factorial, so this is going to be over k factorial plus dot dot dot. Okay, so let's try and simplify each of these terms and see what happens. So we have the 8th in front, 1. Well, the next term is going to be negative 1 over 8. The next term, I've got two negative signs, so they cancel each other out. And the 1 times 2 on the top is exactly the same as the 2 on the bottom. This is now going to be plus 1 over 64, the 8 squared, x to the 6, plus dot 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 plus. Now let's try and deal with this general term. Well, things that we can see straight away, the 1, 2, 3, etc. up to k on the top is exactly the k factorial, but we're left behind loads of negative signs. Well, actually, we're left with exactly k negative signs. And well, that already deals with the minus plus, next term will be a minus, sign swapping that's appearing, and is in the answer. So we're in a good spot already. We then got the bracket thing to the power of k. Well, again, taking a hint from the answer, I'm going to write that 8 as 2 cubed. So I've got 2 cubed to the power of k, x to the power of 3k. So I've simplified that term, plus dot dot dot. Fabulous. And now let's expand out through with the 8th. So we've got the 8th. That's now 1 over 64x cubed. Knowing your powers of 2 is particularly helpful in this question. 8 times 64 gets you to 512. X to the 6 plus all the way to our general term, which has already actually been simplified quite a lot. But now I have the denominator with an extra times by 8, which is just incrementing the power here by 3. Plus dot dot dot. Okay, so I've done the first part, find the binomial expansion. So now let's see how that's actually going to relate to what the question really wanted us to do, which was evaluate this integral. So now this integral between 0 and 1 of x to the m, and I'm going to pre-prepare what I know I'm about to do by rewriting the integral just a little bit as x to the m, 8 plus 3x to the minus 1. So now I know that this is the integral of between 0 and 1 of x to the m. And now I'm going to use this expansion that I've already got above, and I'm actually going to write it as its summation rather than writing it in an expanded out form. So this is the sum. We start our sum at 0, going all the way to infinity, and our general term is minus 1 to the k over 2 to the 3k plus 1. I'm now going to actually factorize that as the answer appears to have done for me. X to the 3k dx. And now this isn't something we worry about at A level, but there is a really delicate interaction between integrals and infinite summations, which most of the time will cause some real big headaches. However, we notice in the question, it did tell us we need not consider any issues of convergence. So actually we don't care about the convergence. And what that actually ends up meaning is we can swap the summation and the integral. Rather than integrating an infinite sum, we can do the infinite sum of all of the separate integrals. So by swapping this over, we can actually bring the x's together. And again, this is really hinted at very closely by the answer, the fact that we've got a denominator of 3k plus m plus 1. That is the power that we have here, increased by 1. So this is now the summation from 0 to infinity of the minus 1 to the k of all this stuff, increase the power by 1, divide by the new power between the limits of 1 and 0. Really nice thing when you have these polynomial style integrals, when you sub in 0, everything gets cancelled. And we should at least check a little bit that this power is always bigger than 1. Because if this power was 0, then it would be 0 to the power of 0. But that's really bad. And really, we should have actually checked it here, because this rule is really bad if this power was indeed, well, if it was -1, we increase and we divide by 0. If it's 0, no, that one's okay. So this thing is greater than or equal to, well, k is greater than or equal to 0, m is greater than or equal to 0, so this thing is greater than or equal to 0, so the rule works fine. And then down here, it's greater than or equal to 1. So we do indeed have an x. If we didn't have an x, then subbing in the 0 would have been a bad time. Because we do have an x, when we sub in 0, it gets destroyed. And we're left with exactly what the question wanted as required. Okay, so we've done this general family of integrals, a power of x over 8 plus x cubed. Oh, Lord. There's a typo right there. Let's fix that. Plus x cubed. Doesn't impact any of the rest of the question, luckily. And we've rewritten it as this infinite sum. Okay, well, let's look at part 2 then. Part 2, in the order it's written, looks like we're going the other way. And if we do look really carefully at this, it does indeed look like 3 copies of part I. So we have the integral of -1 to the k of 2 to the 3k plus 1 over 3k plus 3 minus 2 lots of plus 4 lots of. Okay, well, let's analyze each of these terms, see if we can spot how they link with the first part. Well, this one is exactly when m is 0. We've got the 3k, we've got the plus 1, the plus m isn't needed, so that's when m is 0, that's when m is 1, and that is when m is 2. Great, so we can just use part I of the question 3 times. Of course, being a little bit careful with the coefficients in there. So this is by part I. This thing is going to be equal to, well, the first term didn't have any bonus stuff, so this is the integral from 0 to 1 of x squared over x cubed. Try and write that a bit nicer. X squared over x cubed plus 8. The second term has a -2 on the top, so let's factor that out. And this is now just x over x cubed plus 8. And the third term plus 4 lots of the integral between 1 and 0 of now x to the power of 0. So this is just 1 over x cubed plus 8. Okay, well, I did rip these integrals apart. Again, I've actually used the hidden ideas of convergence in order to rip the summation apart. But now we can put them all back together because we all have the same limits. We have the same denominator. So over x cubed plus 8. And we're having x squared minus 2x plus 4 when I put the components back together. Well, that's not the same as the answer we have. The answer is just an x plus 2. But we have a quadratic over a cubic, so maybe this simplifies. So I'm going to think off to the side whether we can actually simplify these. And if we actually look at the x cubed plus 8, well, a cube number plus 8 equaling 0, well, you could do negative 2 cubed plus 8 would equal 0. Well, that says negative 2 is a root, which means x plus 2 is a factor. A little hidden bit of the factor theorem coming in there to justify. So x plus 2 has to be a factor, so let's build the leftovers. To make the x cubed, we have to have an x squared. That gives me 2x squared, but I don't want any x squared, so I need a minus 2x to go with that x. But now I have a minus 4x that I didn't want, so I need to get rid of that. So I need a plus 4. And then if we check the final term, we do indeed get the plus 8 that we wanted. But notice that that extra quadratic factor is exactly the quadratic factor that's appeared on the top. They really like to design these step questions to magic into anything that you require from them. So therefore, this is equal to 1 over the factor that didn't cancel, the 1 over x plus 2. And now it actually feels like an absolute gimme for the rest of this question. It's now asking you to evaluate this integral. If we integrate 1 over something, we're getting ln, officially ln of the modulus, but here we're subbing in positive limits, so that modulus didn't actually really matter. Subbing these in, we're getting ln 3 minus ln 2. Notice this time when we subbed in the 0, it didn't just make 0. Careful you don't fall into that trap. That only works with nice polynomial integrands, and we get an answer of ln 3 over 2. Okay, cool. We've managed to evaluate this horrendous looking limit into something that's actually really quite pleasant. Final part of the question then. It's asking us to do the same again. We have a different sum which doesn't look like the form we want. But I kind of hinted at this already. There is another technique that will turn this into something more pleasant. We know we're expecting, or we're hoping, for that front term, the negative 1 to the k over 2 to the power, but we want it to be times by a fraction, a simple 1 over, or actually could be any integer, as we saw in the previous part of the question, but over a linear factor. And if we look at the factors we have at the moment, we have a quadratic factor of the denominator, which has the two components looking like a 3k plus something. So this is actually encouraging us to make this into partial fractions. So let's give it a go. So we have this thing. So I'm going to say let that equal, and I don't know what the factors are at the moment, so I'm going to give them some unknowns. So it's 3 over plus, sorry, a over plus b over. Now, if that's true, we can multiply up. So I've got the 72 2k plus 1 equaling a lots of the 3k plus 2 needs to join that fraction, and the 3k plus 1 needs to join the b. Now, if I had a calculator, then I would very quickly just sub in negative a third, which will destroy the b, and see what that equals and solve for a, and then sub in negative 2/3 to destroy the a factor to work out the b. Now, because STEP is a non-calculator paper, I don't really want to sub in negative a third into this. It's doable. I will get an answer. It might just take me a little bit longer and it's slightly more error prone. So I'm actually going to use the other technique of comparing coefficients. This will lead to a simultaneous equation, but I'm slightly more confident solving simple simultaneous equations than I am subbing in ridiculous values. So I'm going to look at the k values on the left, 72 times 2. On the right, I've got 3a plus 3b as my k coefficients. And I do know that 144 divided by 3 is 36. Nope. 40. Well, 3 lots of 3 lots of 40 is 120, 48. There we go. I know it was a multiple of 12 of some form. Is equal to a plus b. I'm then going to look at the constant term. I like to call the constant term something to the power 0, so we know that's just a number. So the constant term here is 72 equals 2a plus b on the other side. This is equation 1, equation 2. My b's line up perfectly, so if I do equation 2 subtract equation 1, that's going to be 24 is the difference. The 2a minus the a and the b's cancel, so I've got my a value, and then equation 1 would then imply that b is also 24. Okay, so I've put this in partial fraction form. So now let's actually try and evaluate this summation. So our summation k equals 0 to infinity of the stuff of the 72 over 2k plus 1 over the double bracket can now be written as, again, I'm taking that very first thing the question says of not worrying about convergence to split this into two summations. I can say it's 24 lots of the sum of the negative 1 to the k, and k equals 0 to infinity, of 2 to the power of the a term that I have above in my partial fraction, plus 24 lots of the sum from 0 to infinity of negative 1 to the k over 2 to the power, and then the fraction that's actually here is 1 over 3 to the k plus 2. Well, now I can use part A of the question again. Really get used to in step questions repeatedly using the same early part in almost every single part in all sorts of magical different ways. So part I of the question is then meaning the first integral is going to be the integral between 0 and 1 of 24. Well, that was when m was 0, so it's just 24 over x, 8 plus x cubed plus 24x, integral of 8 plus x cubed dx. How did that really help? But all I've done at the moment is just try and almost autopiloted for what the question has been hinting me to do. So now I need to try and do this integral. Is there anything clever? I can certainly put it together as one integral. I can have it as 24 plus 24x over the thing. I would quite like the numerator, if I can make the numerator look like 3x squared, well, that will integrate to a Lund term. And I'm expecting a Lund term in my answer. I'm a little bit worried why I'm getting a pi root a. Where's a pi coming from? Well, there's one possibility for that. It could be coming from a trig style substitution. We have a few trig style substitutions that we could be hinting at here. Particularly, I'm thinking about the tan inverse or sine inverse integrals, which are given in our formula booklet. So maybe I need to try and enforce this to be something over a quadratic. Well, that would be quite nice. But that's maybe not obvious either. I'm going to smash these together and start thinking how I could... It almost feels like I need to split this into two integrals. An integral leading to the pi root a, and a different integral leading to a Lund term. Well, I'm going to look back at my factorization that I had for x cubed plus 8 up here. See if there's anything sneaky. Is there any way we could use this again? So in part double I of the question, it was the quadratic factor that disappeared. Or maybe I can make the linear factor. Make the linear factor disappear. Well, that means that the numerator here needs to look like an x plus 2, some multiple of it. And then I can cancel the x plus 2 out of the top and the bottom. So it looks like I could have 24 lots of x plus 2. That gives me a plus 48, so I'll then subtract off 24. So I can rewrite the numerator like that. Now, does that help? Well, on this section, the x plus 2's will cancel. And that will leave me with a quadratic factor on the denominator, and number over quadratic is one of the nice trig inverse integrals. But then I also have that. And that's not giving me the Lund term, which I was hoping for. So what else could I do instead? This looks like it's going to get me stuck. It will give me the tan inverse integral, but it's not giving me the Lund term. Could I do... I'm now looking back to part 2 of the question. Can I link it to what I had here in particular? Because that gave me the Lund term eventually. So could I... Now that does also look quite unpleasant, because then I've got an x squared that's coming in, but we already know an x squared over would lead to another Lund. So that's not terrible. But then I could maybe write it as 6 lots of the x squared minus 2x plus 4. That will make the 24 that I wanted. But then I've got minus 12, but I want a positive 24x. So I need to add 36x and minus 6 squared to get back to like what I wanted. And then the first term is good, because the first term is part double I of the question. The last term is good, because that looks like the derivative over the original. But then the 36x over, that's a little less, it's a little less happy. So I've got 2 techniques here, neither of which seem to have done what I've wanted. I am just keep looking back at the question, keep thinking, how are these linked? I'm also going to take a moment and check some of my arithmetic in other parts of the questions. I do think I agree with my A and B as the numerators to the partial fractions. They look okay. They certainly solve the equations I created. Are the equations I created the correct equations? Possibly. They seem to have done all right. So what have I missed out on? We have... So I'm going to try some other stuff. Let's try and simplify our notation first, because the integral that we really care about, and if we could work this out, we'll work everything out. So I'm going to give it another name, and then I'll turn the page and try. So I'm going to let I be the integral of x plus 1 over 8 plus x cubed. Notice all I've done is taken out that pesky factor of 24. I might regret that later. I might want the 24, but I can come back and put it back in later, and that will be okay. But right now, I'm a little worried. Well, I know that I want a Lund term, but maybe I'm getting the Lund term not from an x squared over the x cubed plus 8, but maybe I'm getting the Lund term from a 1 over x plus 2. So maybe I'm doing partial fractions. Again, this time into the x plus 1 and 8 plus x cubed. Because that'll also give me the other thing I want, which is a fraction with the x squared minus 2x plus 4 as a denominator. So let's try that. So let the x plus 1 over the x cubed plus 8. Let's partial fraction this. We know we're going to have a factor of x plus 2 and a factor with the x squared minus 2x plus 4. Now, if you have a quadratic factor on the denominator, your numerator needs to be linear, which will then mean that the x plus 1, by clearing the denominators, is a lots of the quadratic factor. And you can confirm to yourself that this quadratic factor does not factorize into 2 linear. Probably easiest to justify is by solving that. It only has one real root. The other 2 roots are complex. And now I want to find the a, b, and c. Again, I could only compare coefficients, but actually subbing in a particular x value here is pleasant enough without a calculator. So if x is -2, the left-hand side is -1, equals a lots of, if I sub -2 into that bracket, I'm getting 4 plus 4 plus 4. Nice. Which is going to simplify quite nicely. So the a is -1/12. And this is where I'm slightly regretting losing that 24 factor that I took away to make life easier. And of course, I probably should have said that this term is 0, so it's destroying the bx plus c. If we compare other stuff, let's look at the x squared term. There is no x squared term on that side. On this side, it's a plus b, which means b is going to be -a is 1/12. I could look at the x or the constant term. I'm going to look at the constant term because it's just easier to expand out the double bracket at the end. Constant term is 1, is 4a plus 2c. 4a is -1/3, so I'm adding on 1/3. So that's 4/3 equals 2c. So c is 2/3. And I'm going to check the linear term just for my own sanity. So the linear term was 1, should be -2a plus 2b plus c. So that's going to be 2/12 plus 2/12 plus 2/3, which is 8/12. Yes, that works. The last equation worked. I'm convinced that my a, b, and c are fine. So I'm now actually going to go straight back to here and put the 24 back. Because of all these fractions, I know the 24 is going to be quite useful. So now this I, which was 24 lots of the integral, is now the integral of, well, the 24 times the 12th is going to give me a -2 over x plus 2 between the limits. That looks like it's going to give me the Lund term, plus the integral between 0 and 1. Let's do 24 times the bx plus c. So that's going to be 2x. 24 times 2/3 is plus 8. Nope. Plus 16. 2/3 of 24 is 16. Over the x squared minus 2x plus 4. Okay. Well, I get the Lund term from the first. I could now separate this into a Lund term where I pull off the top, make a 2x squared minus 2x style thing and be able to manipulate that. I think I'm going to have to. So actually the ln term came from two separate parts. So I'm going to have this as the integral between 0 and 1 of negative 2 over x plus 2 dx. I want this to be the integral between 0 and 1 of 2x minus 2, because that's the derivative of the denominator. But in order to do that, well, I want actually a plus 16 on the top, so I need a plus 18 over the thing. And I'm actually going to also prep this into a complete the square form, because I know that's the useful way for these inverse trig integrals. So this is going to be negative 2 ln x plus 2 for the first term. We're going to have plus ln x squared minus 2x plus 4 for the second term. And again, I really should have modulus brackets there rather than the normal brackets, but the limits are both when that denominator is positive, so we're good. Plus. Now this one, I need to go look up the formula booklet. You do get given the formula booklet. If you know these integrals off the top of your head, brilliant. But I would definitely be checking them anyway, even if you do think you know them. So I'm looking for the integrals. Yeah. So I have an x squared plus 3. Yeah. So from the formula booklet, we have the fact that the integral of 1 over a squared plus x squared is equal to 1 over a tan inverse of x over a. So this term, the a is being root 3. This is going to be 18 over root 3. Tan inverse, we've had a translation here of, well, instead of having x, we've got x minus 1. This is tan inverse of x minus 1 over root 3. Now I'm a little worried here because this is a non-calculator paper. I'm less worried because we've got the exact angle looking thing of 1 over root 3. So subbing these limits in, we're getting negative 2 ln 3 plus, if I sub 1 into the next bracket, that's going to be 5. That's going to be plus ln 3. Well, that's convenient. Those can combine together in a moment. Plus, well, this is now tan inverse of 0, which is exactly 0. Minus, when I sub 0 into it, negative 2 ln 2. Subbing 0 into the next term is a plus ln 2. And the final one, the one that we should be slightly scared about, is the 18 over root 3 of tan inverse of negative 1 over root 3. That is a little bit scary. I'm going to deal with things which aren't scary first. So I've got a negative ln 3 from the first bracket. I've got a negative ln 2, but with a negative in front, so that's plus ln 2 plus 18 over root 3. Now let's worry about this tan inverse of 1 over root 3. So this is coming from a 60-30 triangle. That side's 2, that side's 1, that side's root 3. So tan of 30 is the opposite over adjacent, so that's 1 over root 3. But of course this should really be in radians. Using the tan graph, we need to try and find the equivalent negative root. So if that one there is 30, I actually want the symmetric one down here. So that's saying that distance there is 30, so that distance there is 30. that's at 180. Really, I should be working in radians, so that's actually at pi, and that's pi by 6. So I'm going back by pi by 6. So that solution there is 5 pi by 6. Am I convinced? I think so. So this is now times by 5 pi by 6. I was pausing just marginally because I know my answer is pi root a, and particularly a is an integer. So I'm hoping a lot of this stuff in that final term cancels out really nicely. And I might actually have to force stuff into the surd that doesn't naturally want to sit in the surd. Simplifying the final step, we can collect the lunds together, thinking of it more as ln 2 minus ln 3 rather than negative ln 3 plus ln 2. Plus, well, we can rationalise that surd, and 18 over root 3 is 6 root 3 times top by root 3 and cancelling. The 6 is cancelled, so this is 5 root 3 pi. And to write it in the form they wanted, we do indeed need to shove that 5 into the square root. As it goes into square root, it becomes a 25 plus ln. Well, this is worrying again, because I wanted minus ln b. And I don't currently have a ln of an integer. I don't even have minus an integer. So it was actually the ln term which I've made some error in somewhere. So I'm going to go back up. I'm going to check my working carefully. Subbing 1 into the limits, I do get minus 2 ln 3. Subbing 1 into the second of these, I'm getting 1 minus 2 plus 4, which is a plus, which is a ln 3. Subbing 0 in, I am again getting what I want. This here is definitely minus ln 2. This one, no, that does become a positive ln 2. So do I have a sign error elsewhere? The a did come out to be negative a 12th. So we do need this negative here, leading to the negative in front of the ln. This term doesn't give me any negatives. So why am I not getting an integer in there? And again, you're probably spotting this error yourselves while watching this much better than there it is. It's this term over here, which I was a bit too hasty with. When I sub in 0 into this, I'm getting ln 4, but ln 4 is 2 root 2, so there is no 2 ln 2 here. So this does just stay as negative ln 3. So minus ln 3. There's my final answer. A equals 75, B equals 3, comparing the solution that I have. And we've got there. A really surprising question in that we've managed to evaluate this truly horrendous summation that really does not look like it should be attackable in any way, but we've built up a technique, we've used the technique in another way, and then we've had to adapt the technique to get all the way to the end of a summation which really shouldn't be doable. And this is the kind of techniques which mathematicians do have to do while analysing these kind of functions. This function could legitimately have come from a physics problem, an astronomy problem, even probably a biological or chemistry problem where an iterative process is happening, which is producing this force, this rate of reaction, whatever it might be, and we need to evaluate this. We could evaluate it with approximation techniques, or we could actually get the exact value using some of these miraculously inventive ideas coming through. So that's the end of this video. If you are carrying on with this step paper, good luck. And please do watch the rest of the videos down in this playlist as you need them. A quick correction to the end of this question. And well done again if you spotted it before the end here. When evaluating this tan inverse, we should be looking for the principal value, not this obtuse value, which I ended up finding. So really we should have been looking for the solution on this side, the principal value of tan being between negative pi by 2 and pi by 2. So actually this here needs to be the symmetric opposite, which for the tan curve you are rotationally symmetric, so this should be negative pi by 6, which actually makes the question more pleasant. And there was a sign error that I didn't spot originally, that this should be minus that, which makes a double sign error, making this back to being the plus, but no 5. So actually we didn't need to undo and recertify anything. It was just pi root 3. There shouldn't have been that 5 there. And there was a sign error in there as well. I'm hoping that's the only error. If you did spot any more, please do let me know.